So till now we assumed the different phases of our instruction cycle having the same delay 10 nanoseconds. But in practical scenarios, the different phases of the instruction cycle may be having varying delays. For example, suppose our fetch unit take 10 nanoseconds to complete its processing, decode unit take 8 nanoseconds, execute unit take 12 nanoseconds, and write back unit take 10 nanoseconds. And consider the state of pipeline where our instruction I1 is being executed, instruction I2 is being decoded, and instruction I3 is being fetched. We know that in pipelining we organize the entire functional units into separate independent units where each independent unit produces some results upon which the next independent unit can work on. So here the decode unit will work on instruction I2 and produce the results within the time period of 8 nanoseconds. So within 8 nanosecond time period, the results from the decode unit is ready, but the execute unit which is working on instruction I1 need 4 nanoseconds more to complete the execution. Hence, even though the results from the decode unit are ready, the execute unit is not ready to accept the results from the decode unit. Hence, this kind of organization definitely requires some interstage buffer in between the independent units to keep the intermediate results. So in our pipeline system, each subunit is associated with an input buffer, and each subunit associated with its input buffer can be called as a stage. So the use of these interstage buffers in between the independent unit will produce some additional buffer delays in addition to the processing delay. Hence, the total stage delay is the sum of the processing delay within that stage and the buffer delay within that stage. Hence, stage 1 delay is 10 plus 1, 11 nanoseconds. Stage 2 delay is 9 nanoseconds. Stage 3 delay is 13 nanoseconds. And stage 4 delay is 11 nanoseconds. Within each stage, when the processing is over, every stage transfers its results to the input buffer of the next stage. And this transfer should take place at the same time. Hence, a single clock pulse is connected to all the input buffers so that every stage transfers the results to the input buffer of the next stage for each clock pulse. And this transfer time should be such that it should provide enough time for every stage to complete its processing. Hence, the period of clock pulse is determined based on the stage which requires longest delay. Suppose the period of clock pulse is set to 11 nanoseconds. So from now on, within a time period of 11 nanoseconds, stage 1 will complete its processing. Stage 2 also will complete its processing. Stage 4 also will complete its processing. But stage 3 cannot complete its processing within 11 nanoseconds. Hence, the period of clock pulse is determined based on the longest stage delay. Here the longest stage delay is 13 nanoseconds. Hence, the period of clock pulse is set to 13 nanoseconds. So our clock period is 13 nanoseconds. In the first clock cycle, in our first clock cycle, for the 13 nanosecond, the instruction I1 is being fetched now. At the next clock pulse, the results of I1 fetch will be transferred to the decode unit. At the same time, the fetch unit starts fetching instruction I2. And at next clock pulse, the results of I1 decode are transferred to the execute unit. The results of I2 fetch will be transferred to the decode unit, and the fetch unit start fetching instruction I3. In the next clock cycle period of 13 nanoseconds, I1 will be written back, I2 will be executed, I3 will be decoded, and I4 will be fetched. And at the end of the fourth clock cycle, instruction I1 processing will be over. And in the next clock cycle, I2 is written back, I3 is executed, I4 is decoded, and I5 is fetched. And in the next clock cycle, we will get instruction I2. And at the end of 6th clock cycle, instruction I3 is processed out. At the end of 7th clock cycle, instruction I4 is processed out. If we consider the execution of each individual instruction, we can see the execution of each individual instruction takes 4 clock cycles, where the clock period is set to the longest stage delay. So here the execution of each individual instruction takes 4 into clock cycle period, which is 4 into 13 nanoseconds, which is 52 nanoseconds. But if we are using non-pipelined approach, we are not having interstage buffers and we are not setting the clock period as the longest stage delay. The time taken for each individual instruction in non-pipelined approach is 10 plus 8 plus 12 plus 10, which is 40 nanoseconds. So we will get the first instruction processed out in non-pipelining at 40 nanoseconds. Again, in another 40 nanoseconds, we will get the next instruction out. The next instruction will be out in 120 nanoseconds, means another 40 nanoseconds. To process out the next instruction, again another 40 nanoseconds to process out the fourth instruction, and so on. And in pipelining, the first instruction is out at the end of the fourth clock cycle, means at 4 into 13 nanoseconds, which is 52 nanoseconds. So the first instruction is out only at 52 nanoseconds. From then on, for every clock we are getting one instruction out, means in every 13 nanoseconds we are getting one instruction out. It means the time taken for each individual instruction can be more in pipelining compared to non-pipelined approach. Also, to fill the pipeline, the time taken will be more. Here we are getting the first instruction out only at 52 nanoseconds. In non-pipelining, we are getting the first instruction out in 40 nanoseconds. But in non-pipelining, then non every instruction is out at every 40 nanoseconds. But here, in every 13 nanoseconds, we are getting one instruction out. In other words, once the pipe is filled in pipeline approach, we get one instruction out in every clock cycle, where the clock cycle period is set to the longest stage delay. Here in 80 nanoseconds, we are processing just 2 instructions, and here in 91 nanoseconds, we are processing 4 instructions. So the throughput and the speed up is more in pipelining compared to non-pipelined approach. Anyway, the time taken to fill the pipeline, the time taken to drain the pipeline, the variation in the delays, the use of interstage buffer, the choice of the clock period based on the longest stage delay. All these are some factors which will affect the efficiency of pipelining, by which we cannot get the expected throughput and the expected speed up.